Hello everyone, this is part 10 of Econometrics and we're going to revisit the assumptions. In this video, we'll talk about how the assumptions can fail to hold to be true and we'll go over the problems that we're going to face. I would like to mention that you're going to find slightly different assumptions depending on different sources or textbooks. The ones that I've shown contain all the assumptions that I've gathered from different textbooks. So these were the assumptions that we were working with all along. And we'll go over each assumption one by one. I will talk about assumption number 4 first, because this is the one that should have come first in the list. If you remember, I told you in one of the previous videos already that this is our 4th one in our list simply because I forgot to talk about it first. So if you think about this assumption, this is about the structure of the econometrics model. That's why in regards to this assumption, some instructors will simply say something like, our model is the following, where y is going to be explained by k number of x variables and the betas are the coefficients we're interested in estimating. Of course, the reason why we only have one x variable in this video is because we're working on simple linear regression. So then now the main question is, how can this assumption fail to hold and what are the consequences? Consider this relationship between y and x in the middle. This model is not linear in parameters, and so standard econometrics method, the OLS method that we've been using so far, cannot be used here. If this is the true relationship between y and x, then you will not get the correct results if you assume a model like the one on top. How about this one? This model is linear in parameters, and so OLS method can be used for this model. But this model is saying that y and x have non-linear relationship. If this is true, then assuming a model like the one on top will not get you the correct results since the model on top is assuming that y and x have a linear relationship. So the bottom line is that if you're assuming a model that looks like this, then you're good to start estimating the betas if the true relationship between y and x follows the model on top. Okay, let's move on to the next assumption, which is random sampling. What happens if the data points or observations are not IID? Well, if the data points are not IID, then UI from 1 through n are not going to be IID. To see why this is going to be a problem, let's first understand what UI represents. The easiest way to understand UI is to think about it as a combination of all the factors that affect yi, except for the variables that you are already considering in the model. So y should really be yi here, y variable for individual I. And now we'll go over an example to better understand UI. So this is a model we're considering in our example, with exam score being the y variable and hours of study being the x variable. This means that the error or UI in this model represents some combination of all the factors that affect the exam score for student I, except for the variable hours studied. Now suppose that the true model is this one. So exam score actually depends on 2 variables, hours of studied and the focus level of a student. Of course, in reality, exam score should really depend on more variables, and there should also probably be a nonlinear relationship between the exam score and some of the x variables. But for simplicity, let's just assume that this is the true model. Well, in that case, since all the variables are already controlled for in this true model, the error in this model, or the epsilon, is going to be random. And that is good because we want errors to be as random as possible. What about the error UI in our original model? Well, it's easy to see that this portion represents UI because we have omitted the variable focus in our original model. So UI is going to equal to this term at the bottom, which is basically some combination of the variable focus and the random component. So that's what I mean by combination of all the factors. UI represents combination of everything that affects the y variable except for the variable that's already included in your model. And it's easy to see that since UI contains the variable focus, UI is not going to be random obviously, and that may lead to all sorts of problems as we're going to see throughout this video. So that's what errors are, and they may be random or not depending on your model. Next, we're going to see how the errors can fail to be IID, which means that assumption number 1, the random sampling, is going to be violated. Okay, so we'll continue to use our UI here, which depends on the variable focus level of a student. Note that If focus level is correlated across some students, then errors will be correlated across some students. In other words, errors of some students will tend to be high or low together. And all of this means that errors are not going to be independent. I'll give you a made-up example. You were supposed to collect data points randomly across students in US. But suppose data points are mostly from one town. Also suppose that students in that town are forced to take some sort of meditation practices together from time to time that increase their focus for a while. This means that focus level of students will be correlated, which finally means that correlation of focus level between student I and J is going to be non-zero for most of the different pairs of I and J. And so this also means that correlation between UI and UJ is also going to be non-zero for most of the different pairs of I and J. And all of this means that UI for I equals 1 through n are not going to be IID, since most of the UIs will be correlated with one another. So this was a quick example of how random sampling assumption can be violated and how errors can fail to be IID. And now the question is, what kind of problems do we face if errors are not IID? If you look back at one of my videos, you can find this set of equations for the conditional variance of beta 1 hat. And if you remember, we were able to go from this line to this line because the errors were assumed to be independent. If the errors are not independent, then variance of the sum is not equal to the sum of the variances. We also have to consider the covariance between the errors. And so if the errors are not IID, one problem that we're going to definitely have is that the condition of variance of our main estimator, and when I say main estimator, I'm talking about beta 1 hat. So condition of variance of our beta 1 hat will not be correctly calculated if we incorrectly assume that errors are IID when in fact they are not. Your t-stat will be incorrectly calculated and you may draw wrong conclusions about statistical significance. So this is our first problem, and there may be other problems as well, but this is the most obvious one. Okay, let's go to our next assumption. Our next assumption says that large outliers are unlikely. So then what happens if we do have large outliers? In terms of math, without this assumption, beta 1 hat does not converge to the true value with large N. Intuitively, if we assume that large outliers are likely, and if large outliers are to be included in your analysis, then our estimates will be unreliable because estimates are sensitive to large outliers. Another way to think about this is to ask yourself, if large outliers are likely, how will you ever be sure about the estimates when you know that estimates may change wildly with different samples? Our next assumption is about zero conditional mean assumption. If this assumption does not hold, then beta 1 hat may be biased and inconsistent, making estimates unreliable. There are many ways this assumption can fail to hold, but I'll talk about the one researchers are usually concerned about, and it's called omitted variable bias. So what exactly is omitted variable bias and how do we get it? Well, there are two conditions that are needed for omitted variable bias to occur. The first condition is that you do not include or you omit in your analysis the variable or variables that affect the y variable. And the second condition is that the omitted variable or omitted variables are correlated with the variable already included in your model. So these are the two conditions needed for omitted variable bias to occur. And before moving on, I want to make a note about the second condition here. I want to make it clear that if you have more than one omitted variable, for instance, if you have 3 omitted variables, you don't need all 3 omitted variables to be correlated with the variable of interest for there to be omitted variable bias. In other words, even if just one of the 3 omitted variables is correlated with variable of interest, then you're going to have omitted variable bias. Okay, so then what are the consequences of having this problem? Well, the third assumption is going to be violated. But more importantly, beta 1 hat will not be reliable, meaning it's going to be biased and inconsistent. Now I'll show a bit more detail about omitted variable bias using math. Let's first bring back the setting where the true model includes 2 variables, but we use this model instead where we only have one x variable, our studied, and so our UI now includes the variable focus. Before moving on, I want to make a note that for this exercise on omitted variable bias, for simplicity, you can just consider the scenario where you have a random sample, and thus the errors are IID. So the important thing to note here in this exercise is that the variable focus is omitted from our model. It's not included in the model. Okay, so then coming back to our setting here, I'm now going to get into the mathematical detail to show omitted variable bias. To do that, let's first suppose that there is some correlation between the variable's focus and our studied. And of course, that means that there is some non-zero covariance between the two variables. And in this case, covariance between UI and ours is also not going to be 0, which means covariance between UI and XI is not 0. I'm just changing notation here since in our original model, the only XI is our studied. Of course, the variable focus is another X variable, but to avoid confusion, when we say XI, we mean our studied in these videos. Also, these variables here should really have I subscripts, so it's a typo. Now, in part 4 and 5 videos, I talk about how our third assumption implies zero covariance between UI and XI. This means that if covariance between UI and XI is not 0, then it must mean that expected value of UI given XI is not going to be 0. And finally, this also means that our third assumption is going to be violated. So then what is the consequence of all of this? Well, in our setting where the variable focus was omitted from our analysis, and also assuming that there is some correlation between the two variables focus and our studied, then beta 1 hat would not be reliable, meaning it's going to be biased and inconsistent. So that is the consequence. And now to show exactly why beta 1 hat is going to be biased, I'm going to use this equation, which is the equation that you already saw before in one of the previous videos. So as you can see from this equation, beta 1 hat is going to be unbiased if expected value of UI given XI equals 0. But in our particular setting, UI depends on the variable focus, which means that the expected value of UI given XI equals this term underlined in blue. Now note that expected value of focus given our studied is going to depend on our studied if there is some covariance between the variable's focus and our studied. In other words, expected value of the variable focus given our studied is going to be some function of our studied. Expected value of epsilon given our studied is simply going to equal to 0. I included additional information in the description section of this video as to why this term is 0. So in the YouTube channel, in the description section of this video, you can read about it. So at the end, expected value of UI given XI is going to be some function of our studied. We actually know what that function is, but I do not want to get into too much detail here at this point. So then now what all of this means is that this term in the equation is non-zero since it's going to be some function of our studied, which then means this entire term is not 0 and therefore beta 1 hat is going to be biased. Now, let's see exactly why beta 1 hat is not consistent under this particular setting where the variable focus was omitted. I'm first going to pull up this equation, which is showing that beta 1 hat converges to this term. You already saw this equation in one of the previous videos as well. Now, if you look at this term in the numerator, this is covariance between UI and XI. So in our particular setting, if there is some covariance between the variables focus and our studied, then there's going to be some covariance between UI and XI, which means that this term in the numerator is not going to equal to 0, and therefore, in our setting where the variable focus was omitted from our analysis, and also if there is some correlation between the two variables focus and our studied, beta 1 hat is going to be inconsistent. So what's the lesson here? The lesson is that if you're interested in getting a reliable estimate for the causal effect of our studied on exam scores, you want to include all the variables that affect exam scores, since most likely those omitted variables are correlated with our studied. So then this model here with 4 variables would definitely be a better model. So this model is now saying that exam score depends on our studied, focus level of a student, IQ, and wealth of a student. But even with this new model, how do we know we've controlled for all the important variables affecting exam scores? Also, this model is too simple. It does not even consider nonlinear relationships between y and some x variables. So we can never be sure that we have the absolute correct model, and if we do not have the correct model, then this third assumption will be violated and some or all the estimates of the coefficients or the betas will be unreliable. Most likely, there will be some criticism about your model. The bottom line is that your model may be close to the true correct model, but there may also be many doubts. And this is why researchers are always careful with interpretations. For instance, suppose the beta 1 hat of this new model with 4 variables is 0.07 and also you pass the statistical significance test. Then researchers would say something like, for each additional hour of studying, exam score increases by 0.07 on average, controlling for other variables. Note that this statement is about a positive relationship rather than a cause and effect. This is what I mean when I say researchers are careful with interpretations because they're not going to be 100% sure that they have the causal effect. In most situations, we need more sophisticated econometrics methods to claim causal effect. Okay, next one is our fifth assumption, which says that the variance of ui given xi equals some constant number, which we call sigma squared. And if you remember, this fifth assumption can be seen from this graph of population data, since the dispersion of ui given any xi is shown to be the same. So this would be an example of how the fifth assumption can fail to hold because it's clear that the variance of ui is higher when the values of x are also high. In other words, in this graph, variance of ui given xi is not constant. It changes with different values of x. Okay, so then let's go over the consequence when this assumption fails to hold. Well, let's first pull up this condition of variance equation from one of the past videos. Note that we have sigma squared here because of our assumption. So if our assumption does not hold, then condition of variance should be different than the one we have calculated before. The bottom line is condition of variance of our main estimator, and I'm talking about beta 1 hat here. So condition of variance of beta 1 hat will not be correctly calculated if we incorrectly assume that assumption 5 holds, when in fact it does not. Your t-stat will be incorrectly calculated, and you may draw wrong conclusions about statistical significance. Now we're going to talk about our last assumption, which is about normality of ui. So needless to say, if errors are not normally distributed, this assumption will fail to hold. So then the question is, what happens if this assumption is violated? Our t-test, statistical significance test, was based on the assumption that errors are normally distributed. So if errors are not normally distributed, you may draw wrong conclusions about statistical significance. So this would be the consequence or a potential problem. So that's everything I wanted to talk about our assumptions in this video. And finally, I would like to say something about all the videos on econometrics that I've posted on my YouTube channel. Up to now, I think I covered about 20% of what you would learn from an introductory level econometrics course in universities. Some schools, they're going to be more mathematically rigorous than my slides, while some other schools will focus more on intuition. I believe I covered both intuition and math with fine detail, step by step. If you understood everything in my slides, then you'll be good to go for the remaining material in econometrics course in any school, or most schools. The remaining 80% of the material is mostly about adding more regressors, modifying assumptions, and then doing a whole lot of algebra and memorizations of formulas, and so on and so forth. Of course, when you get to higher level econometrics, you get to do more advanced stuff with linear algebra and more math to give you more headaches. For now, in my YouTube channel, I think this video is going to be the last video on econometrics. But if you want to see more videos on econometrics, please leave a comment and of course, I'll make some more.